Imagine the coldest cold possible, a cold so deep it makes Earth's harshest winter feel like a summer day. This is the realm of absolute zero. It's not just a very low number on a thermometer, it's a fundamental limit set by the laws of the universe. Absolute zero, or 0 Kelvin, is the point where the universe runs out of heat. It's the floor of temperature, a limit you can get close to but never truly reach. At this point, the tiny frantic dance of atoms and molecules that we sense as heat almost completely stops. It's the quietest state matter can achieve. When we talk about heat, we're really talking about motion. The atoms in your chair, the air you breathe, the stars in the sky, they're all vibrating, jiggling and moving. This microscopic chaos is what we measure as temperature. A hot object is one where its tiny parts are buzzing with tremendous energy, bumping and zooming around. A cold object is one where that dance has slowed to a gentle sway. But as you keep taking away energy, that movement slows down more and more until, at the edge of absolute zero, the particles have given up almost all their movement energy. They become still, quieted into a state of the lowest possible energy. This idea is more than just a fun fact. It's a key part of how we understand energy and matter. It tells us that heat isn't some mysterious liquid flowing between things, but the total energy of countless tiny particles moving. Every object in the universe, with a temperature above absolute zero, holds this inner heat energy. From the fiery heart of a distant sun to a forgotten ice cube melting in a glass, this energy is a sign of existence itself. Reaching absolute zero would mean silencing this inner hum of the universe, achieving a state of deep, quiet calm. The journey to absolute zero has been one of the great adventures of modern science. Labs around the world use fancy lasers and magnetic traps to cool atoms to just a tiny bit above this final limit. In these super cold conditions, matter starts to act in weird and wonderful ways, showing us the deep quantum rules that control reality. Even though we might never perfectly reach absolute zero, our quest to get as close as possible keeps pushing the boundaries of what we know about the universe and the basic nature of energy itself. It's a reminder that even in looking for extreme cold, we find new and amazing ways to discover things. Now let's explore a fascinating though speculative idea. What if that thermal energy, the very jiggling of atoms we just talked about, actually adds to an object's weight? This is the main idea behind a concept called the Thermal-Gravitational Expansion Theory, or TGET. This theory asks us to think differently about what gravity sees when it pulls on an object. It suggests that gravity doesn't just interact with the fixed mass of protons and neutrons, but also with the energy inside the object. According to this idea, the more thermal energy an object has, the more it should weigh. It's a bold connection between the worlds of the very big, like gravity, and the very small, like atomic motion. The TGET says that when you heat an object, you're doing more than just making its particles wiggle faster. You're in a way filling it up with energy. This added energy, the theory claims, has a gravitational signature. Think of it this way. Einstein's famous equation, E equals mc squared, tells us that mass and energy are two sides of the same coin. The TGET takes this a step further by suggesting that the E from thermal energy should add to the m that gravity interacts with. So, a hot potato full of thermal energy would pull on gravity a tiny bit more than an identical cold potato. Let's use a simple example to understand this. Imagine you have a sealed box full of buzzing bees. The bees are constantly flying around, bumping into the sides, bottom and top of the box. Their constant energetic bumps would create a tiny, continuous downward force, making the box feel a little heavier than if the bees were all resting quietly at the bottom. In this example, the bees are like the atoms and their frantic buzzing is the thermal energy. The TGT suggests that the universe works in a similar way. An object's internal energy adds a tiny, almost impossible to notice, amount to its total weight. This idea goes against what we usually feel and see every day. We don't notice our coffee cup getting heavier as we fill it with hot coffee, or our ice cream getting lighter as it melts. The TGT knows this, saying that the effect is incredibly small, too subtle to be measured with regular scales. However, it brings up a deep question about the relationship between two of the most basic forces in the universe, gravity and thermodynamics. It suggests that every time we light a fire or cool a drink, we are, in some tiny way, changing how it interacts with the gravitational fabric of space-time. If heating an object adds a tiny bit of weight according to TTG, then the opposite must also be true. As you cool an object, systematically removing its internal thermal energy, its weight should go down. The frantic dance of its atoms slows, their contribution to the object's gravitational presence lessens, and the scale, in theory, would register a lower number. Every degree of temperature you drop would correspond to a tiny reduction in weight. This process of losing weight as it cools would continue as you go lower and lower on the temperature scale, marching toward the ultimate limit. This leads to a surprising prediction at the very bottom of the temperature scale. What happens when you finally reach absolute zero? According to the logic of TTG, this is the point where an object would have its lightest possible weight. At 0 Kelvin, all the thermal energy that contributed to its weight has been removed. The vibrating atoms are now fundamentally still, stripped of all of their heat-related motion. The gravitational signature of that thermal energy would completely disappear, leaving only the weight that comes from its bare resting mass. The object would have lost all its thermal weight. Think of a sponge soaked with water. The soaked sponge is heavy. As you wring it out, the water drains away and the sponge becomes progressively lighter. The water represents the thermal energy, and wringing it out is like cooling the object. When you've squeezed out every last drop, the sponge is at its lightest weight. This is its dry weight. Similarly, an object at absolute zero, according to TTG, has been squeezed of all its thermal energy, leaving only its fundamental or dry weight. This leftover weight comes purely from its basic matter, with no extra contribution from heat energy. This idea gives us a fascinating and real-world outcome for a theoretical concept. It's one thing to say that energy has weight, but it's another to suggest a specific, though extreme situation where we might actually see this. The difference in weight between a rock at room temperature and that same rock at absolute zero would be incredibly tiny, probably impossible to measure with our current technology. However, the prediction itself is a big deal. It suggests that an object's weight isn't just a fixed, unchanging thing, but something that subtly changes with its temperature and its energetic dance with the universe. How does this idea from TTG compare to what we already know about the universe? In classic physics, the world of Isaac Newton, weight is simply mass multiplied by the pull of gravity. Mass is thought of as a constant, unchanging property of an object. Whether a cannonball is hot or cold, its mass and so its weight stays the same. The idea that heat energy could change weight doesn't fit into this neat mechanical picture of the universe. The classic view keeps the worlds of gravity and heat separate. It's a simple, powerful model, but it might not be the whole story. When we move into the world of quantum physics and Einstein's relativity, things get more interesting. We know from E equals mc squared that energy and mass can be swapped. For example, the center of an atom weighs a tiny bit less than the total of its individual protons and neutrons because some of its mass has turned into the glue-like energy that holds them together. So, modern physics does agree that energy can have a mass equivalent. However, the part that heat energy plays in an object's total mass is usually thought to be so incredibly small that it's ignored for almost all practical uses. The special thing about TTG is that it raises this tiny effect to a main rule of gravity. The thermal-gravitational expansion theory is still a new idea, a guess that needs to be carefully tested. The predicted change in weight is so tiny that finding it would need tools much more sensitive than what we have now. But that's how science moves forward. We build what we know on things we can test. TTG offers one of those predictions, asking future scientists to come up with clever ways to prove it right or wrong. Whether it turns out to be right or not, its value is in making us ask deeper questions. In the end, exploring ideas like TTG is what science is all about. It encourages us to look at the universe with fresh eyes and to question our deepest beliefs. Could the warmth of a star and the pull of its gravity be more closely linked than we ever thought? Does every object in the universe have a weight that changes slightly with its temperature? These questions make us feel more amazed and remind us that there are still huge, unknown areas in how we understand gravity, energy, and the very fabric of space and time. The universe is waiting for us to ask the next question.